Okay, so here comes this theorem I want to ask you about. Suppose somebody comes along and they tell you, well, you know, here's a vector v, and I'm going to have an operator, linear operator, acting on this space. So the operator is going to be t, and I'm going to act on the vector v. And moreover, I find that this is 0 for all vectors, v belonging to the vector space. And the question is, what can we say about this operator? For all vectors, it's just 0. So is this operator 0 maybe? Does it have to be 0? Can it be something else? Okay, we've been talking about real and complex vector spaces, and you know, we've seen that it's different. The inner product is a little different. But let's think about this. Take 2 dimensions, real vector space. The operator that takes any vector and rotates it by 90 degrees. That's a linear operator. And that is a non-trivial linear operator, and it gives you 0. So case settled. There's no theorem here. There's nothing you can say about this operator. It may be non-zero. But here comes the catch. If you're talking complex vector spaces, t is 0. It just is 0. Can't be anything else. Complex vector spaces are different. You can't quite do that thing, rotate all vectors by something and do things. So that's the theorem we want to understand. Theorem, let V be a complex inner product space. By that, it's a complex vector space with an inner product. Then V, TV equals 0 for all V implies that the operator is just 0. That I traced a lot of my confusions in quantum mechanics to not knowing about this theorem. That somehow I was saying, it must be true. I don't know why it should be true, but somehow it's not, because it really has an exception. So here it is. We tried to prove that. It's so important, I think, that it should be proven. And how could you prove that? And at first sight, it seems it's going to be difficult, because if I do just a formal proof, how is it going to prove know that I'm not talking real or complex vector spaces? So it must make a crucial difference in the proof, whether it's real or complex. So this property really sets the complex vector spaces quite apart from the real ones. So let's see what you would need to do. Well, here is the strategy. Suppose I could prove, if I could prove that U, U TV is equal to 0 for all U and all V. You see, the problem here is that these two are the same vector. They're all vectors, but they're the same vector. If I could prove that this is 0 for all U and V, then what would I say? I would say, oh, if this is 0 for all U and V, then pick U equal to TV, and then you find that TV is 0. Therefore, TV is the 0 vector. by the axiom of the inner product. For all v is a zero vector, so t kills all vectors, therefore t is 0. So if I could prove this is true, I would be done. Now, of course, that's a difficulty. Well, I wouldn't say of course. Takes a leap of faith to believe that this is the way you're going to prove that. You could try to prove this, and then it would follow. But maybe that's difficult to prove. But actually, that's possible to prove. But how could you ever prove that this is true? You could prove it if you could somehow rewrite u of t, u and tv as some sort of maybe something with a t and something plus some other thing with a t and that other thing plus all kinds of things like that, because the things in which this is the same as that are 0. So if you can do that, if you could re-express this left-hand side as a sum of things of that kind, that would be 0. So let's try. So what can you try? You could put u plus v here and t of u plus v. That would be 0 because that's a vector, same vector here. But that's not equal to this because it has the UTU and it has the VTV and has this in different order. So maybe we can subtract u minus v t of u minus v. Well, we're getting there, but so all this is question marks. UTU, VTV, this cancel, UTU, VTV. But the cross products, what are they? Well, here you have a UTV, and here you have a VTU, and do they cancel? No, let's see, UTV, and here is U minus TV, but there's another minus, there's another one there. And VTU has a minus, but minus a plus. So actually, this gives me 2 of this plus 2 of that. OK, it shouldn't have been so easy anyway. So here is where you have to have the small inspiration. Somehow, it shouldn't have worked. You know, if this had worked, the theorem would read different. You could use a real vector space. Nothing is imaginary there. So the fact that you have a complex vector space might help. So somehow you have to put i's there. So let's try i's here. So you put u plus iv and t of u plus iv. Well, then we probably have to subtract things as well. So u minus iv, t of u minus iv, these things would be 0 because of the general structure, the same operator here as here. And let's see what they are. Well, there's UTU, and here is minus UTU, so the diagonal things go away. The minus IV, minus IV, and a T, you have minus IV is subtracted, so that also cancels. So there's the cross products. Now, you would say, well, just like the minus signs, you're not going to get anything because you're going to get 2 and 2. Let's see. Let's see what we get with this one. You get U with TIV. So you get I, U, TV. But look, this I on the left, however, when you take it out, becomes a minus I. So you get minus I, V, TU. And the other products cancel, so let's look what you get here. A u with a minus iv, and a minus here gives you a 2 here. And the other term, VTU, well, this goes out as a plus I, but with a minus, it becomes a minus I, so VTU is this, so there's a 2 here. So that's what these terms give you. And now you've succeeded. Why? Because the relative sign is negative. So who cares here? You can divide by I and divide this by I. You're constructing something. So let me put here what you get. I can erase this blackboard. So what do we get? I claim that if you put 1/4 of u plus v t u plus v minus u minus v t of u minus v, then let's see, what do we need to keep? We need to keep u and tv. So divide this by I plus 1 over I u plus iv t of u plus iv minus 1 over I u minus iv t of u minus iv, and close it. So you've divided by I, you get here 4 of these ones, 0 of these ones, and you got the answer you wanted. So this whole thing is written like that, and now, since this is equal to u with tv, by the conditions of the theorem, any vector here, vector, 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 these are all 0. You've shown that this is 0, and therefore the operator is 0. And you should be very satisfied, because the proof made use of the fact that it was a complex vector space. Otherwise, you could not add vectors with an imaginary number, and the imaginary number made it all work. So the theorem is there. It's a pretty useful theorem, so let's use it for the most obvious application. People say that whenever you find that VTV is real for all V, then this operator is Hermitian or self-adjoint. That is, then it implies T dagger equals T. So let's show that. So let's take VTV, proof. You take VTV, and now is equal, this thing is real. So since this is real, you can say it's equal to VTV star. Now, because it's real, that's the assumption, the number is real. Now the star of an inner product is T V, V. But on the other hand, this operator, by the definition of adjoint, can be moved here, and this is equal to T dagger V, V. So now you have that this is equal to this. So if you put it to one side, you get that T dagger minus T on V times V is equal to 0, or since any vector that, any inner product that is 0, its complex conjugate is 0, so you can write it as V, T dagger minus T of V is 0 for all V. And so this is actually a well-known statement that any operator that gives you real things must be Hermitian, but it's not obvious because that theorem is not obvious. And now you can use the theorem and say, well, since this is true for all V, T dagger minus T is 0 and T dagger is equal to T. Then you can also show, of course, if T dagger is equal to T, this thing is real. So in fact, this arrow is both ways, and this way is very easy, but this way uses this theorem. There's another kind of operators that are called unitary operators. We'll talk a little more about them next time, and they preserve the norm of vectors. People define them from you, and you see that they preserve the norm of vectors. On the other hand, you sometimes find an operator that preserves every norm. Is it unitary? You say, yes, must be. How do you prove it? You need, again, that theorem. So this theorem is really quite fundamental to understand the properties of operators, and we'll continue that next time. All right.